Hi everyone, my name is Finch. Today I'm gonna explain about multiple regression in Excel. So this is our raw data. It has two independent variables called R studied and sleep quality, while one dependent variable called the score. So to start with this, we have to make a summary output. To make that, we have to go to the data data analysis, then choose the regression, then press OK. So, input wire range. So, the input wire range, you should input the test score, our dependent variable, while the X range is the two independent variables. Then check the labels and all of this, check it. So, press OK. So this is the summary output. So the summary output shows the R square 81.80%. So the model explained that 81.80% of the variation in student test scores based on R studied and sleep quality, while the remaining 18.20% is explained by other factors not included in the model. So it also shows the significance. So the significance is less than 0.05. So the overall regression model is statistically significant. This means that the independent variables taken together significantly predicts the student's test score. So it also shows the coefficients. So assuming the other variable remain constant, so one additional R studied, the predicted score increased by about 0.96 points. And 1 unit increase in sleep quality, it increases about 1.99 points. So regression is a statistically method used to predict the value of a dependent variable based on one or more independent variables. So it estimates the best possible prediction using the available data. So in summary, the multiple regression analysis shows that the model is significantly statistical, indicating that our study and sleep quality together significantly predict students' test score. The model explained 81.80% of the variation in the test score, while the remaining 18.20% is influenced by other factors not included in the model. Among the predictors, R studied has the significant positive effects on test score, whereas sleep quality has a positive but not statistically significant effect. Overall, the findings suggest that increasing study hours is the strongest predictor of the better academic performance in the dataset. So, the expected test score if R studied is 40 and the sleep quality is 7. So, to get the expected score, we have to use this equation or formula. So, the intercept coefficient plus the coefficient of R studied times 40 plus coefficient of sleep quality times 7. So the output of that is 56.90%. So the trend. Calculate expected mark for table. So to get the trend one or the expected marks for the table of this table is to use the trend. So to use the trend, we have to select first the known y, which is our test score. Next is the known x, which is the studied R studied and sleep quality. So the since we don't have new x, we have to leave it blank, then the constant is true. So by that we can get the trend. of this equation. So in this new table, to get the second trend, calculate the expected mark for the new table. So to get that, we still gonna use the same formula of the trend 1, but the new x gonna use the new table. So the new table, so the R studied x1 and the sleep quality x2. So this is the formula. So the output is this. And next is the residuals. So the residuals is the difference between the actual value and the predicted value. So to get the residuals, so you just have to minus the actual score from the predicted score, which is the test score minus the trend Q1. So you can get these outcomes.
So now, multiple regression in Python. I start by importing 3 libraries such as pandas, StatModels, and scikit-learn's linear regression. Here, I load the CSV file. Now, my original file wasn't clean. It had extra content from Excel, like trend and forecast tables, sitting in the same sheet as my raw data. So this second line slices the data down to just the first 15 rows and first 3 columns, which is where my actual dataset lives. Next, I renamed the columns. The original headers had spaces and symbols like X1, which are inconvenient to reference in code, so I gave them simple, clean names instead. So next, the line converts every column to numeric values. This step was necessary because pandas initially read the column as text. That's because before I slide the data, the same column further down contained the text labels like trend. This line parses everything into proper numbers, so the model can actually calculate it with them. Next, preparing the variables. Here, I split the data into 2 parts. X holds independent variables. The predictors are studied and sleep quality. Y holds dependent variable, which is the test score, which is what I'm trying to predict. Next, this is the core of the analysis. The first line adds a constant term to X. This represents the intercept or the baseline score when both predictors are 0. StatsModels requires these steps explicitly. It doesn't add it automatically. The second line actually builds the regression model using a method called ordinary least squares, or OLS. This is the standard method for multiple regression. It finds the line, or in the case plane, that minimizes the total squared distance between the predicted scores and the actual scores. Then this prints the full regression report, the same kind of output you'd see from Excel data analysis. It includes the coefficients, standard errors, p-values, r-squared, and the f-statistics. And this line just put out and display specific numbers from the report individually. The coefficients r-squared adjust r-squared and the f-statistics with its p-value, so I can reference them directly in this presentation. So here's the OLS regression results. Coefficients Q, cortices, and coefficients R squared and adjusted R squared F statistics. Here, I build the second models using scikit-learn. Just to confirm my results, the FIT method is where the model actually learns. It looks at all my data points and calculates the best fitting intercept and coefficient. Then this line print out Skylearn's version of the same numbers, intercept, coefficients, and R squared, so I can compare them side by side with the stat model's output. So, making a prediction, now I test the model on a new hypothetical student, someone who studied 40 hours and has a sleep quality rating of 7. I create a small data frame with those values, then ask both models to predict what test score that student would get. I run it through both models to check that they produce the same answer. And this is just print both predictors so I can compare them. Here, I calculated the residuals, the difference between each student's actual test score and the score the model predicted for them. A residual close to 0 means the model predicted the student well. A large residual means the model missed by a wide margin. I print out the full table so I can see student by student where the model over or under predicted. I also print the sum, mean, and standard deviation of the residuals. The sum and mean of the residuals are both to count 0. This is the expected with also regression since it's built to balance out the errors. The standard deviation 7.53 tells me roughly how far off typical prediction is in percentage points. Finally, I plot the residuals against the predicted scores. This is a standard diagnostic check. I'm looking to see whenever the points scatter randomly above and below the 0 line, or whenever there is an obvious pattern like a curve or funnel shape. A random scatter supports the idea that a linear model was a reasonable choice for this data. So, this one, the trend one, these sections build a simpler single variable regression, the kind of trend line exhaust trend functions produces using only R studied as the predictor and setting sleep quality aside entirely. This lets me see how much predictive power R studied has on its own. So, this gives an intercept 14.01 at a slope of 1.0 and an R squared of 0.8095. In other words, on its own, our study already explained about 81% of variation in test scores, almost as much as the full two variables models 82%. So I plot the actual data points alongside this trend line so the relationship is visible at glance. As R studied increases, test scores rise in a clear, fairly tight linear pattern. So the next is the thread 2. This mirrors the thread 1, but isolates sleep quality instead, leaving R studied out of the picture. Here's the intercept is negative 14.60, the slope is 10.67, and the r squared is only 0.4106. So sleep quality by itself explains about 41% of variation in test scores. Noticeables weaker than our studied on its own. The lines up with what we already saw in the full model. Sleep quality has a real positive relationship with test scores, but it's a much less reliable predictor than our studied, and its effect mostly overlaps with what our studied already explained. Again, I plot the actual points against this trend line. The upward slope is visible, but the points scatter more loosely around it than they did for r studied, visually confirming the lower r squared. And a note on statistical significance. With only 15 observations and 2 predictors, check the p-values in the stats model summary above. A predictor is generally considered statistically significant at the 5% level if its p-value less than 0.05. Predictors with p greater than equals to 0.05 should be interpreted with caution, even if the overall model's F-test prob F statistics above is significant.
So, multiple regression. So, what is multiple regression? A statistical method used to predict one dependent variable using 2 or more independent variables. It helps determine how several factors together affect an outcome. So based on our example data, we have one dependent variable called test score and 2 independent variables are studied and sleep quality. So this is our data sample. It has 15 rows of data. So regression equation. Regression formula models the relation between a dependent variable and one or more independent variable to predict an outcome or estimated effect. So, where our x1 is r studied and x2 is sleep quality. So, each number in front of a factor is a coefficient. How much that factor pushes the score up or down. So, to get the coefficient, you have to make a summary output and you will get the coefficients. So this is. So go back to our presentation. So the forecast. Example of this to predict an answer or a test score. So example of this, the given is R studied is 30 and sleep quality is 7. So using the formula, we can get the predicted test score. So just change the x1 to 40 and the x2 to 7 to get the predicted test score of is 56.90. This means a student with these values is expected to score approximately 56.90%.
So now, predicted scores. Trend calculates the predicted scores using the regression equation. It was used to calculate predicted scores for the original dataset or Trend 1. Predict scores for the new datasets or Trend 2. So here's the Trend 1 and Trend 2. And the residuals, the equation of residuals is the actual scores minus predicted scores. This means the residuals measures the predictions error. Positive residuals is actual score is higher than predicted. Negative residuals is the actual score is lower than predicted. Residual close to zero is predictions is accurate. So now, R-squared shows the models explain 81.80% of the variations in students' test scores based on our study and sleep quality. The remaining 18.20% is explained by the other factors are not included in the model.
Example of this, two students has equal study hours in sleep quality, but their test score is different. This may cause from the other factor that not included in the model. Example of this is stress, attendance, and etc. that may affect the test scores.
ANOVA shows the significance less than 0.05, which means the regression model is statistically significant. This means the independent variables taken together significantly predict students' test scores. And now, lastly, summary. The multiple regression analysis shown that the model significantly predicts student test scores. The model explains approximately 81.80% of the variations in test scores. Regression is a statistical method used to predict the value of a dependent variable based on one or more independent variables. It estimates the best possible predictions using the available data.